took that intro with us too, right?
All right.
It just made me think.
So let's get started. You guys all ready?
Because I started in the front, I couldn't I didn't even realize who was in the class. You know what I mean? Like if you sit in the back, you can see everyone
All right.
in front of you.
I'm going to start talking now. So welcome to Exgal for today. Today is day 3 out of 30 something, 27 I think. Okay, reading 1 came in. Oh, I got to get those out. Y'all did a great job. I really appreciate all the questions that everybody asked. The pandemic weirdly killed everybody's ability to ask questions. It was really weird. But I feel like I got all these great questions now. So I feel like, I don't know. I appreciate it. I like the questions that you guys asked during the reading section. That's the entire reason that I put those up. It makes me feel like it's more of a dialogue between us rather than just me standing up here talking, which I like talking, so I don't mind. But this way I can like fix all the things that are missing. And also, one of the things this book does is it defines things implicitly. It just starts using terms and doesn't ever say extinction is blah. This thing is blah. It never really like comes out with a good definition of this stuff. That's a running theme throughout the book. So if ever you're like, I read that whole section and I still don't know what extinction is. Use that as an example because like half of you asked about the reddening and the extinction. That's understandable, it's tricky. So some of the bits in here, like some of the questions I know are coming. So the moving cluster thing, nobody understands that because the book isn't that great and you're still not gonna understand it because I don't care about it. So I'll show you some cartoons so that you're not totally in the dark, and if you want to go back and work out the math from my cartoons, you can sort it out. But the math is like, it's like a bunch of trig, and then you're like, well, do I still get it? And then the next day you forget it. So I'll show it to you real fast. But then other things, like I don't know that you're missing, that you don't get something, or you didn't understand something when you're reading, so I really appreciate everybody's questions. So I'm going to go through questions first. I used to type them up. I didn't this time. So I'm just going to go through them. Okay, so the first question. In the galactic coordinate systems that we were talking about, here, let me put this on me so that, because I'm just talking. In the galactic coordinate system, is the sun or the galactic center the origin of the system? And the answer is, it depends on which coordinate system you're using. And it depends on, really, what you're trying to measure. And what are you trying to measure with respect to what else? So most of the time, the sun is at the center of the coordinate system because it's easier to measure from where I am. If 0 is me, then that is positive. That's easy to do. It's really tricky to measure distances from the center of the galaxy, and we'll spend a whole day on this. In a couple of weeks. How do you measure distances with respect to the center of the galaxy? It's actually very difficult. But if I'm talking about a galaxy, and I'm talking about the dynamics of the galaxy, it doesn't make sense to put the center somewhere other than the center of rotation of the galaxy. So it depends on the coordinate system that you're using. Now I feel like there was another question. If I get to it, there was another question about the coordinates. And again, while I'm going through a question, you can feel free to holler and have me slow down and go over a bit more. My answer right now doesn't help. Okay, so the origin depends on where you need it to be, is the short answer. What is the near IR band? So the near IR band is the near infrared band. So that means, yeah.
Is spherical coordinates the one that's like at the center of the galaxy?
Both are usually. Oh, the other one was about cylindrical coordinates.
Which one?
So sometimes
corresponds to what?
We got. It really depends on what you need to be using it for. So the book defined 2 coordinate systems. Where's my camera at? One is centered on. Oh man, I forgot to grab chalk again. I probably left this one here last time. Okay, so we've got this galaxy, and it's a disk. This is the galaxy that we live in. It's got some thickness, which I'll come back to in a second. It's got a center of rotation, and so when I'm dealing with this galaxy, because it's a disk and it's not round, it makes sense to describe this in a cylindrical coordinate system where I talk about the vertical component, the radial component, and the tangential component of whatever quantities. So I've got some angle, I've got some radius, and I've got some vertical. So that's usually the ones that we use for a galaxy. And then if we're trying to talk about where things are in space, then I'll use the celestial coordinate system, which is centered on the Earth. And then, okay, depending on, actually, cylindrical, I can't spell that word, so I'm just going to write cylindrical, are for when you want to know where something is in the galaxy. Then we have sun-centered. And then you have to say, am I aligning my coordinates up with the galaxy, or am I lining them up with the solar system? Those are two different choices. So we have galactic, or solar system. And this is really about what is the midplane. So the midplane of the solar system is the ecliptic, and it runs at an angle with respect to the galaxy. But when you look up in the sky, kind of everything is lined up along this plane that we live in. So a lot of times when you have a telescope, solar system, sun-centered coordinates are the ones to use. But if I'm trying to find where something is in the galaxy, then I'll use galactic coordinates. So kind of depends on what you need to be doing. Hopefully that'll become more clear as time goes on. Let's see. Near IR band. So this whole electromagnetic, I should have a graphic for this. The whole electromagnetic spectrum spans radio waves, which are, meters long, to X-rays or gamma rays, which are nanometers long. The visible range is from like 2 to 700 nanometers. Near IR is from like 700 nanometers to like 1.2 microns. So it's the infrared that's pretty close to the visible spectrum. That's different from the far infrared, which is longer wavelength stuff. So the spectrum gets broken into radio waves at the longest settings, and these are usually in the meters. Centimeter and millimeter waves, or microwaves. These are shorter than radio, but not quite infrared. Then we have the far IR, and the mid IR, and the near IR. These are just different lengths. So this is like a micron, or this is like 2 microns, and this is like a fraction of a micron. And then we have visible, and this is in a little bit less than a micron to about half a micron. Then we have the UV, and UV is broken into hard and soft. I'm not going to go through all the different subclassifications. And then X-ray, and soft X-rays are almost UV, and hard X-rays are almost gamma rays. And then we have gamma rays. Gamma rays are the shortest wavelength, highest energy photons that we see. What is a CMD? A CMD is the color magnitude diagram. I'm going to spend a little bit of time, not very much, I'm going to spend a little bit of time talking about color magnitude diagrams today. Another name for that is the Hertzsprung-Russell diagram. A CMD and an HRD tell you basically the same thing, but a Hubble of the HR diagram is specifically B luminosity and temperature, whereas the color magnitude diagram is color versus brightness. Now, okay, they're the same, they're similar because temperature and color are related, but they're a little bit different. But you get the same physics out of it. The basic physics is what's going on versus how bright is it. We'll come back to that again. What is birth color? So the birth color is the color of a star when it's born. That seems a little circular, doesn't it? what does that mean? Okay, so in my HR diagram, so the HR diagram is color here and brightness here. And there's this stretch of stuff. So temperature increases in this direction. Why does it go in this direction? Okay, because Hertzsprung and Russell did it as color and magnitudes with specific colors. I think I might have said something slightly incorrect, but now I can't go back and look at what I said. Anyway, both of these are about color and magnitude. The Hertzsprung-Russell diagram are particular colors, but the important bit, temperature increases this way. Bluer is this way. Bluer is a smaller number. I'll come back to this in a second. Right. The HR diagram tells me about color versus brightness, and things move on this. So something is born way up here pretty bright, and as they're contracting, what do I mean by born? Let's just start with that. What do I mean by a star is born? That means it lands here on the main sequence. Once it gets here, it starts burning hydrogen into helium. That's what it's on the main sequence. Before it's on the main sequence, it's somewhere else in this diagram, not quite hot enough to burn hydrogen into helium. It's hot enough to burn deuterium, but somewhere else on this diagram, it's actually up here, and they come down this way. They just go straight down. The color doesn't change, but they get dimmer because they get smaller. And then they catch on fire. The nuclear burning starts, the hydrogen burning starts, and then they're on the main sequence. So that's the birth color. Then they will evolve. So they will evolve in here somewhere as the star ages. As the star ages, its color changes, just like everything else. You know, if you've got, your hair when you were a little kid was blonde, and now it's brunette or whatever. So things change color as they age. Then at the end of their lifetime, they'll go way up here and turn into a supergiant or something like that. But the birth color is where they land on the main sequence. So I'll come back to that a little bit more later. Okay, reddening is in the visual. Are there other bands that are also shifted? That's a really good question. Typically, we talk about the reddening just in the visual band because higher frequency bands are blocked completely by the dust, so they don't have this reddening effect, they're just gone. So you can't see X-rays through the dust. You can't really see UV through the dust. You just can't see it. You can see some of the visible through the dust, and that's why we talk about extinction. And then the infrared, it doesn't really change much at all because the photons go right past the dust. And then in the radio and the centimeter waves, those photons don't care about the dust, so it goes right through. So weirdly, we only talk about this reddening in this one visual band. It's this kind of collusion of annoyances. The universe created all this dust, and it happens to be right in the middle of the frequency range where we see. So it's just kind of coincidental. How do we determine the composition of the dust? I can't answer that question right now because it's kind of complicated. The short answer is they look at spectra. So really the answer for everything, how do you learn that from outer space? We look at spectra. So they look at infrared spectra of dusty clouds, and they back out what the dust has to look like. And it turns out you can say, so we start with a blackbody diagram, or with a blackbody curve, and then we modify it in certain ways to make it not look like a blackbody anymore, because now we've got absorption and re-emission. And from fitting the spectra, they can sort out what the dust is. The actual answer is it's kind of a mess, and we don't really know what the dust looks like. But I'll show you some pictures of what we think interstellar dust looks like. That was a good question. Some of you have very nice handwriting. Okay, the radiative transfer equation. A couple of you commented that were confused when you got to that radiative transfer bit. I'm going to go through all of that in a little bit simpler way that makes a lot more sense. It doesn't invoke bigger guns. The radiative transfer equation is kind of horrible. No, it's not really, but it's a much bigger gun than I want right now. So I can do it at the end of the day if I got a minute. but I'm probably not going to have a minute. So at some point in time, I'll talk about the radiative transfer equation again, but I don't need it right now. It's more than I want. So we'll come back to that. Some examples would help. I'll try to do that. Somebody said just more examples, please. If you have specific things that you want examples on, you can throw those in there. Like, could I see an example of X? That'll help me out. Let's see. Are there other objects that are used for determining distances other than stars? We talk about stars, but yeah, we can use all of this works for galaxies or black holes as long as you can see them and measure them, then you can get the distance to them. Some things are actually really a pain in the ass to get the distance to, though, like big fluffy clouds of gas that are far away. It's really hard to say how far away they are. But other more compact objects, like actually black holes are kind of tricky, but stars are pretty easy. Black holes you can do, and we'll talk about that. Some black holes you can do really easily, clear across the entire goddamn universe. We'll talk about those too. Those are pretty cool. So yeah, all kinds of objects. What is extinction? I'll talk about that. It's just things getting darker because there's stuff in the way. But I got some better graphics for that coming up. How are distances specified in spherical coordinates? So that's a good question. So the dumbest answer is, here's my spherical coordinate system. Here's me at the sun. And the distance is just the radial coordinate. Outside of that, if I want the distance from, because I need it, here's me at the sun. Here's the galactic center. If I want this distance here from the galactic center to some other object, say I need to know how far. So say this is me, and I'm looking at this star. I want to know how far this star is from the galactic center. That's hard, and it takes me 10 minutes to derive it. So we'll get to that better. So distance in spherical coordinates, in these coordinates we'll talk about more later. What are the units on magnitudes? What are the units on magnitudes?
Isn't it like a logarithmic, like?
It's a log of something. So what's the units of it? No, it's the log of something. So what are the units of it? It's unitless. You can't put units into a log. You can't get units back out of a log. So they're dimensionless. That's a super important question. I really appreciate that question because units tell you like 80% of the physics. You can do 80% of all the physics that you ever want to do just working out the units. So that's a really good question. These are dimensionless, so that goes out the window. But very good question. Thank you. What is this color excess business? I'll talk about that. Our relationships like the distance modulus and the period luminosity relation, are they derived or are they observed? That's a great question. Some of both. The distance modulus is just a definition. That's just, here is geometry. I got 1 over r squared kinds of laws. Distance modulus has to look like that. But the period luminosity relation, now we can explain exactly where it comes from. But it was found observationally just by saying, well, there ought to be a relationship between these things. Let's go look and see if there is one. Hey, look, there is one. Oh, hey, this is useful. Oh, hey, let's get an actual answer for this. So the discovery is sometimes comes from the theory first, and sometimes comes from the observation first. Almost always it comes from the observation first, and everything is backed onto that. That's a good question. How do we determine the galactic plane? That's a good question. I will do that when we do where we are in the galaxy. The basic idea is like you measure where everything else is doing, and you say, well, everything has got to be symmetric about the midplane. So we measure everything and say, where is it symmetric? That's the midplane. I'll get into more detail later, but that's a good question. Can we approximate galaxies as two-dimensional? Sometimes not. Depends on how detailed you want to get. A galaxy isn't a two-dimensional object, but they do have a pretty high aspect ratio. So sometimes you can treat them as two-dimensional objects. And so as a astrophysicist, sometimes I do that, and I say, well, okay, a galaxy's a disk, two-dimensional, has some properties. Other times I need to know what's going on inside that disk, in which case it's very three-dimensional. So it depends on how much accuracy you want. That's a good question. Can we go through the moving cluster? Yes, very short. Also extinction and reddening? Yes, soon. Moving cluster. One of you said, I need to look at each equation in depth. And I like that statement. But no, it's great. So yes and no. So I would like for you guys, when you're going through and you get to an equation, read that equation like it were a sentence in English, because that's how it's written. And that's how the journal, like when you're writing a paper for a journal, they say equations are like sentences in English. They get punctuated just like everything else. And you should read it like a sentence. Some of these equations are really heavy to really understand where it comes from and what all the pieces are doing. So yeah, whenever it comes across that equation, take a look at it, try to read it like English, and say this is related to this by way of this, and try to think what are the things that are related. But sometimes that's heavy, so don't kill yourself on it. That answer? So I really like that statement. I think it's really clear. I will do the radiative transfer equation later. Would you call reddening redshift? This is a great question because no, but it looks the same very much a lot. So when I see a thing get redder, until I do more work, I don't know if it got redder because there's dirt in the way or because it's moving really fast. So we'll talk about that in a little detail. You can tell, but you can tell the difference. Once you get a spectrum, then you can really tell. Let me draw a picture of something real quick. So say I got this spectrum. With a spectrum, you can tell everything. If you don't have a spectrum, then it's harder to tell. So what's a spectrum tell you? So this is wavelength versus flux in some weird fluxy units. So okay, they're going to be in like ergs per second per square centimeter, something like that. But the units don't matter. Like I could have them in magnitudes. It could be a lot of things. So I got some spectrum. And let's say that this is the Lyman alpha. And this is swirl button. What's Lyman alpha? 13, 16? So okay, lambda is swirl brain is not telling you what the wavelength of Lyman alpha is, but we're going to say it's 1300 nanometers. It's not quite. So I've got this line. If I don't call it Lyman alpha, it doesn't matter what it is. It's just a line at 1300. I've got this line radiation in my cloud that is coming off at this frequency. This is what I observe. Now, if I happen to get a telescope close to that object, and it has a spectrum that looks like this, and I can see it's shifted in wavelength, then that's redshift because of the motion. But if it's like this, oh no, sorry. Yeah, suppress the blue. So this one is bluer because I have a lot less short wavelength stuff, but the peak is in the same spot. So now you have to be able to see the peak of the radiation as a function of wavelength to be able to tell if it got redder because it just looks that way or because it's really moving. I'll do this again in like 2 minutes, maybe 8. Are all globular clusters from the early universe, or are there new ones? I don't know. I have never actually asked that question, so now I really don't know. I don't know what's the youngest globular cluster. I have no idea. I love that question, because I have no idea how to answer it. Well, I know how to answer it, I just can't right now. I have to go look, but I didn't have time. But that's a great question. Why is the center different in the different coordinate systems? This kind of depends on what you're trying to measure. The coordinate system should present itself. Let's see, extinction and reddening. How was period and luminosity discovered? I don't actually know in detail. I know that they had a bunch of people who were computing fluxes and brightnesses and all kinds of stuff. They had a team of people, and Henrietta Leavitt happened to be bright enough and had enough clarity of vision to make the right image. Virial theorem. Virial theorem is, I'm going to spend an enormous amount of time on virial theorem. But virial theorem is just an expression of force balance. It means all of the forces all got basically balanced. So what it says is, okay, the simplest statement is the absolute value of the potential energy is twice the kinetic energy. So this is no, not most general. This is a generic way to write it. The most general way is much longer. It's like 8 terms in it. There's certain examples, so it's gnarly. The way that I deal with it most is I say v squared equals gm over r. Gravitational binding energy is gmm over r. Kinetic energy is 1/2 mv squared. The 2 goes away because of this 2, and the m goes away, cancels with this m. So we're just left with v squared is g, which is just a number for units, m, the mass of the thing, divided by the size of the thing. We'll come back to this in, oh, I'm not on the board. Come back to this in very detail later. Okay. Now, going back here. Where was I? Yeah. Yeah, so the short answer is you can't, the way I wrote it here. This is why I said I'd just do it later, because it's easier to answer. She asked me this on an email. You need to get the total mass from this, you need to know a little bit more than what I wrote down. So I wrote down that dn dm is proportional to n to the minus 2.35. It really doesn't need to be this many degrees significant digits on this number, because we don't actually know it that accurately, and it's not constrained by the universe accurately enough. But this minus 2.35 is the canon that everybody uses for this number. So because of this proportional to, I can't get the total area under this curve. So what this says is I have a function of m, and I have dn dm, and I have the relationship, but what I need, if I want n is the integral of dn dm over dm. So I just add up this function over m, and I'm left with n. This is just like fundamental theorem of calculus. But because of this proportional to, I didn't tell you where this line is. So depending on where the line is, the area underneath the curve has very different values. So what you need to do is, typically we work with the fractional relationship of things. So what I typically do is say, what is the fraction of stars that are G stars? So we say that G stars are in this mass range. So, and we say, so we need to know an upper limit and a lower limit. The total number of stars is going to be the integral from m1 to m2, the lower limit to the upper limit, m1, m2, of dn, dm, dm. But this is just, if I haven't given you this constant of proportionality, you can just make it up and just say, okay, it is perfectly legal if I have a proportionality to erase that proportionality, just replace it with a constant. Just replace it with a constant, a, or whatever you need. Let's call this so if the question that I ask you, which is a possible question that I might ask you, is what's the fraction of stars that are between, let's say, A and B, then what you would say is the total fraction is equal to the integral from A to B of dn dm over the integral from mass 1 to mass 2, the minimum to the maximum mass in the distribution of the same thing, dn dm dm. Now I got this constant, let's leave this as an a. I've got this constant of proportionality, a, that I don't know what it is. if I look at the fraction, then I've got an A here and an A here, and they cancel out, so it doesn't matter. So if I'm just looking at the fraction of mass or of number, then it doesn't matter. The constant of proportionality doesn't matter. Now, if I tell you that the total mass of the cluster is whatever, then you can get the constant of proportionality. Does that make sense? Yeah.
What are the integral bounds on the top one?
So say the question is, what's the mass fraction in G stars? Then the integral would be the minimum G star mass to the maximum G star mass, for instance. And then this would be the minimum total to the maximum total in my sample. Does that make sense, everybody? Cool, because that question will show up as a homework question tomorrow, I think. Oh, no, it's not on this homework set, but it's on the next one. So when we get to that homework, here's the answer. Come back and look at it. That's all I'm going to say about the IMF. This is a field that you could spend your entire life working on the initial mass function. So magnitudes. Now we're going to talk about magnitudes, which I like to complain about, but it's a pretty useful system. Here is soup. Here is sorted soup. Here is salad. Here's sorted fruit salad. This is an artist. His work is called The Art of Cleanup. The reason that I put this up, because I found these on Reddit right before I started teaching this class, and I came across this one, which has all these stars, and then here they are sorted. Dope. I love this. He sorted all the objects by size, which is exactly what Hipparchus did 2,000 years ago. And he said that these guys here are 1, these guys here are 2, these are 3, these are 4, 5, 6, 7. Now, this is a dumb system, but he didn't know that at the time. He was just like, what the hell is going on in the sky? So this is how magnitudes were born. So flux, F, is what I get out of my telescope. And that's in like ergs per second per square centimeter. Right? Now, flux, for a brighter thing, the flux is a bigger object. So the fact that we're calling the brightest objects 1 and the dimmest objects 7 introduces a minus sign that will be forever confusing. So there's a minus sign that I'm going to complain about a lot. Also, the human body is really kind of magnificent. It has a very wide dynamic range of things that you can see and hear and touch and feel. So you're necessarily a logarithmic sensor. So when you perceive something as twice as bright as another thing, it's actually an order of magnitude more bright. So there's another weird glitch, but that's all right. So everything's in log. Also, these things vary over an enormous range of space. So having things logarithmic is very useful because dealing with numbers like this one has a flux of 100, and this one has a flux of 100,000. It's hard. We just call this one 2 and this one 5. Those numbers make a lot more sense. Okay, so we're left with this. So I didn't have a good pointer when I was in COVID, and I had to do everything with this thing because the pointer didn't work on Zoom at the time. Anyway.
I'm sorry to interrupt,
Yeah.
but I think I have a question. I don't know how to word it.
That's fine.
But like in magnitudes, like when it's very bright, I forgot how it is, but I think it goes to like negative, right?
Yeah,
when
that's
it's
right.
very bright.
Yeah.
Like why does it start at that? Why is the 0 set where it is? You know what I mean?
That's a great question. It's Vega.
Okay, thanks.
That's it. So the 0 point is set relative to the star Vega. Now, actually, we do something that's a little bit more sophisticated and a little bit more careful. So instead of actually pointing at the star Vega, we have a synthetic spectrum of a star that we calibrate everything to. So we said, okay, Vega's doing it with this one random object. It's kind of bad science. So we'll do it with the ensemble statistical A0 star. Regardless, I'm not a stellar astronomer, so I'm just going to say Vega all the time, as that's our fiducial. The fiducials are probably are a lot more sophisticated now. You should take observational techniques next semester, and we'll talk more about those details. So you can see something that's about a 7, and it's all based on Vega. So this is what? So this is M1. This is the magnitude that I need. This is what I measure with my telescope. And M2 is the brightness of Vega. F1 is the flux that I measure from my telescope. F2 is the flux that I get when I measure Vega. Now, one of the nice upshots of this is your telescope is a thing that some dude made, or some lady. Some person made that telescope. It's got glitches and imperfections. And there's the atmosphere, and the temperature changes, and sometimes it rains, and sometimes it's a little sleety, and sometimes there's a little bit of atmospheric dust that you can't really tell. Maybe it's a little hazy. Maybe there's a lot of water in the atmosphere. All kinds of random ass things happen when you're trying to take a picture of a star. So one thing you can do, and one thing that was done a long time, was take a picture of Vega, and then take a picture of the star that you care about, and then take the ratio, and all of the systematic nonsense, how hot your telescope was, whether there's extra garbage in the air, all of that cancels out. So the fact that it's a log and a ratio is actually very important for doing consistent astronomy. However, it's kind of a headache to get your head around. So we've got 2 different kinds of magnitudes. So there's the apparent magnitude, and that's what I see. That's what I measure with my telescope, and that is relative to a fiducial star, which we'll call Vega. There's the absolute magnitude, and that's the magnitude that I would measure if that object were at 10 parsecs, which is a little arbitrary. It doesn't make sense to put it at 0 parsecs because the flux goes like luminosity over the distance squared. So if the distance squared is 0, the universe hates that. You can't divide by 0. So we put it at 10 parsecs. There's very little at 10 parsecs. It's really funny. We live in this bubble where there's really not much going on. We're kind of in the backwoods of the galaxy. There's really nothing going on for like a kiloparsec around us. It's kind of amazing, which is really handy because it lets us see out. If we were in a star cluster, we would see the stars. So the absolute magnitude is if it were at 10 parsecs, and the distance modulus mu is defined as little m minus big M. So that is the apparent brightness, that's what I actually see, versus the absolute brightness, which is what it actually is doing by itself without all this distance. So the apparent magnitude is like the flux, and the absolute brightness is about the luminosity. And then the distance modulus is as if it were at 10 parsecs. Okay, this is 5 log d minus 5. Why is that? It's kind of awful. So this, I got a 2.5 already in my equation. Why is there a 5? Because we get a squared. So little m minus big M is going to be minus 2.5 times the log base 10 of the luminosity over 10 parsecs squared. Or, little m is the luminosity over 10 parsecs squared. This 2 comes out and gives me a minus sign. The minus 2.5 log gives me something that's a big M. So I got big M minus minus gives me a plus log base 10 of 10 parsecs squared, 2.5. The 2.5 comes down and I get plus 5 log 10 of d over 10 parsecs squared. Sorry. The little magnitude is luminosity over d, getting ahead of myself, over d squared. That's the distance. The total magnitude is this if this were 10 parsecs. So if I drop this in here, I get the magnitude minus d over 10 parsecs. D divided by 10 pc squared. So this 10 parsec can come out as 1. So I can write little m minus big M, the distance modulus mu, equals little m minus big M, equals 5 log 10 d over parsec, or over 10 parsecs, or 5 log 10 d over 1 parsec minus 5 You'll see it written in both ways, because the distance is relative to 10 parsecs. But that's not the natural thing to do. If you want the distance in parsecs, then you have to have this extra -5. A little kind of confusing, but just remember this one. And then when I put up this other one, get confused for a second and then remember, oh right, it's because of the 10. Where am I at? So this is the distance modulus. It's just like the magnitude definition. Color, okay. So this so little m equals -2.5 times the log base 10 of the flux over the flux of the fiducial star minus the magnitude of the fiducial star. This is the same thing. It's just defining flux. Now, what I wrote down was for the volumetric. Volumetric means all of it. Oh, I should change my. Stay put. Now, I don't have to use all of it, so this is all of the photons that I get on my telescope. Realistically, this is all of the photons that I get on my telescope, and the ones that my telescope wasn't able to see. So my telescope is not sensitive to microwave. It includes that too. Volumetric includes everything. So what I might want is just part of the color. So say I get a clear sheet of paper, or a clear sheet of plastic that's blue, and I stick it over my telescope. Then I can get the blue magnitude. So the B band magnitude, we're just going to call B for blue, is -2.5 times the log is 10 of the B band flux over the B flux of vega plus the B flux of vega. All I did was took this and changed all my M's to B's. Now, what do I mean by any of this? Well, this is just a definition of what I mean by B. The only thing that's weird is this FB. So what do I mean by FB? Oh, and then this isn't a color, this is a flux. So let's go for a second. I'll come back to this slide. Let's look at some spectra. Oh, I'm going to come back to this slide. This slide's not in the right order. Okay, let's talk about filters. So I'm going to come back to this for a second. So a spectrum is complicated. How do you get a spectrum from a telescope? I think I'm not. Everything's going to slip. Somehow I'm talking slower this semester. So if I don't get through all of the distance stuff by the end of Thursday. Oh no, actually sorry. There's distance stuff on the homework, but I think that it might not be on this homework. So I'll look again. I'm going a little slow. I'm going to keep going this pace because I think it's fine. The homework might slip. I'll look at it again. I don't remember exactly where I put it. Okay, so filters. How do you take a spectra using a modern telescope? So I have, here's the opening of my telescope. Here's me. That's not how telescopes work. You don't sit there anymore. You used to. There used to be telescopes that you could put your head there. Now, I have a CCD. CCD stands for Charged Coupled Device, and it's how you turn electrons into a picture. So, real brief, it's an array of little capacitors, and a photon hits one of these capacitors and drops an electric charge. And then you read that electric charge out and you get a picture. How do I turn that into a spectra? I got to use diffraction. So the simplest way to do it is just to put a plate in front of the telescope. And here's my star that I want to look at. And I'll put a slit right here and look at that telescope, or look at that star. So then on my CCD, what I'll see is the star right here on this pixel, and then say I put the slit in this direction, then I'll see the diffraction pattern off to the sides. Make sense? So then I'll have this pattern of brighter and dimmer and brighter and dimmer, brighter and dimmer in both directions. And then I read this out and I figure out what's on this stripe. That seems kind of labor intensive, right? I got to mill, I got to cut a line in a piece of metal to put it in front of my telescope. I got to take this image and I got to figure out where the line was, figure out which pixels are my spectra, measure the spectra. It's all pretty tricky, and it's time consuming, and it's real estate intensive on your device. So the spectrum needs a lot of space. So, but then what do you get? Let's look at it. So then you get a spectra that looks like this, or whatever it looks like. Oops. Where am I? This is flux. So this is very labor intensive, and I can only do it one star at a time, or one quasar at a time. So like this is one object at a time. How many stars are in this cluster? 10 to the 5. I can't do this 10 to the 5 times. Where's the picture of the dude doing it? So here, I don't know if you can see this picture. This man is plugging in these wires into this plate. Here I've got a fiber optic cable for every star. So that makes me not have to mill this thing, but yeah, it's complicated business. So this guy's got to plug in these fiber optics into everything that you want to take. That's super labor intensive. Well, I want to take the spectra of everything here at once. So what I'll do is I'll just break the spectrum up into filters and just measure the filters. It's like a coarse graining. So instead of having a spectrum, let's look at this bottom picture. This bottom picture is a spectrum of an A star, like Vega. You can see the spectra comes up here and then falls down as you get to higher wavelengths. And we break the visible spectrum into several bands. We've got U, B, V, R, and I. Those are the principal ones that we see a lot. But there are many, many, many different filters. So there's thousands of filters that you can find. But B, V, R, and I are the typical ones that are used today. And we define these as integrals. So how do I do this in real life? So the bulk of the sun is here. Bulk of an A star is in those regions as well. This slide's out of order. So if we look at things in different filters, we can see different galaxies in different colors. And you see different structures in the different colors as well. So I don't remember what telescope these are taken of, but this is the red R, V, and B magnitudes. None of these are colors. These are colors are ratios of these images. Why? I'll get to that in a second. So if I want this, say this image, I get a spectrum that looks like this. I just want this part of the spectrum. Well, this is the R part of the spectrum. So mathematically what I do is I have some transfer function that's my red filter, which we're going to call a Gaussian when we're ever doing math with it, but it might just be a square top hat function. It's really nothing like that. It's like this shape here, and this one here, this guy here. Not perfectly Gaussian, but pretty close. So the B flux, so if this is my spectrum F, the B flux, I'm just going to integrate along wavelength from 0 to infinity. I'm going to add up all of the wavelengths, but I'm going to put in a function. So F of lambda is my spectrum. I'm going to put a function in here that's 0 outside of the band and 1 inside the band. I'm going to call this T of R. So my B flux is just an integral over my flux times this transfer function. Oh, I should have that on the screen. Sorry, the camera's in the wrong spot. There you go. So here's my spectrum. Here is, oh, this is R. We pretend this is B, doesn't make a difference. This is some flux that I care about. Let's call it B. So to find out what the B flux is, I just add up all of this stuff and ignore this stuff and this stuff. So I do that with a transfer function. The transfer function is 1 here and 0 here, more or less. So we just integrate. We integrate over wavelength of the flux times this function, which turns on and turns off, and that gives us our B magnitude. This is not a color yet, because if the object gets further away, this number goes down. But the color of an object shouldn't depend on how far away it is, right? Something that's further away should look the same color as something that's close to you, because empty space doesn't care. Empty space will not change the color of the photons. So the color so here's our transfer function. Here's a bunch of filters. I have some snapshots from some books that have some filters in them. Colors we define as the ratio of the fluxes. Ratio of fluxes means difference in the magnitudes. The reason we do this is to cancel out all of the distance information, so we get the color as something that's intrinsic to the object. So I have my spectrum, F versus wavelength. It's like here, and we'll say that this is R, and this one is V, and this one is B. So R is just an integral over the flux from 0 to infinity, d lambda, f of lambda, t red of lambda. This is 1 here and 0 here. B is 0 to infinity, the flux of lambda times tv of lambda, and V is the same. Then the color that I want, the actual color, is B minus V. This is a ratio. No, it's not. It's a difference. That's one of the magical things about logs. Logs are the coolest thing because they turn addition into multiplication. So here I've got some addition, but really I want it as a multiply. I just take the same, so B equals minus 2.5 times log. I'm going to drop the 10. If I need natural log, I will write ln. But I need mean log base 10. FB over FB fiducial plus B fiducial. And V is going to be minus 2.5 log FV over FV fiducial plus F plus V naught. So then B minus V is going to be minus 2.5 times the log of FV over FV minus the fiducial colors. So we got the fiducial colors, you got the log of FB and FV, and there's another thing in here, we just pack those into here. This is a number that we look up. It's like 0. So my color, B minus V, is the ratio of the fluxes in the two different bands. Log of that, then you got a minus sign to make it a ratio, and then you got to normalize it. This bit doesn't matter as much. This is kind of like 0. I'm only keeping it here to be accurate and consistent. B minus V is minus 2.5 times the log of the ratio of the fluxes. That's the important bit. Okay. So now I have this sheet that you're going to want to come back to. I didn't write this sheet for now. I wrote this sheet for later. This is a bunch of things that look like brightnesses, just so that you can keep track of them. Really, I wrote it so that I could keep track of them. So there's the apparent brightness, where you have the brightness that you measure and the brightness of the reference star. You have the B band brightness, which is the apparent brightness in the B band relative to the reference star. You have the absolute brightness, which is the brightness that I would see if it were at 10 parsecs, and the apparent brightness. We have the distance modulus, and we have the color. And these all will have the same kind of form. Yeah.
So in the color on this one, you have a plus sign, minus B minus T. You have the same here. On the previous page, you have a plus sign there.
It's a number that's like 0, so it might not. It doesn't really matter. Might have to be a plus sign. Damn it. Let's cheat and look in the book. Pretty sure it's in here. But I'll have to get back to you on that. I think it's probably a plus. Because it's a plus here. And it's pluses here. So I think it's a plus, you're right, thank you. Oh, I only have 3 minutes left. Talk about color magnitude diagrams. Okay. Color magnitude diagrams. Does anybody have any questions on color, real quick? Are there other questions on color? We'll spend plenty of time talking about color. Now let's talk about what you do with color. So this is V versus B minus V. This is an HR diagram. And here we see, where's my pointer? This right here is the main sequence. So these are stars that are comfortably burning hydrogen and not doing anything weird. Once stars start to die, they leave, yeah.
So you make like HR diagrams for like certain like little areas of space. You know what I mean? Like,
Yeah.
Okay. I thought it was like a grand scheme of things sort of thing. But is it relative to like what's in that like cluster?
Yeah, exactly. Yeah, that's right. So you make an HR diagram for a region of space, for a population of stars. And you want that population of stars to all be relatively related to each other. Because you can learn a lot about the system, but you need to know, for really interpreting what the HR diagram is, it's really important to know that all these objects were born at the same time. Then I can see what they're doing. So if they were all born at the same time, then I can very easily tell how old this cluster is. Did you guys talk about main cluster turnoff in Astro? Okay, so in this color magnitude diagram, do I have one up still? I meant to leave one up for myself. Okay. So in this color magnitude diagram, in this color magnitude diagram, we've got B minus V and V. I have my main sequence like this, and then I have this snake up here, and I've got these stars and these stars, and maybe I've got some down here. Okay. This is color, but it's also a proxy for temperature. Hotter stuff is over here. Hotter stars die first. That's it. So I just say, what stars do I have? Stars hotter than that are all dead. Stars younger than that are not. And by dead, I mean up here doing their thing. They don't die for a while. They've left the main sequence. So I can tell I can tell the age of the cluster by looking at where I don't have any more stars. This is pretty useful. This is called the main sequence turnoff technique. I'm not going to spend any more time on that because now I'm out of time. Is that? Oh, 12:50. I'm sorry, I was stuck on last year. I still got 15 minutes. Thank you so much. That was great. Man, a less trustworthy class would have let me stop. Okay, so I'm done with this slide deck. I'm going to start the next one. That's great. Okay. Now, distances. I'm going to talk about distances in detail. Okay. I can measure, as an astronomer, I can precisely measure radial velocities, how fast something is moving away from me, pretty well. I mean, super well. I can measure brightnesses very well. I can measure positions in the sky very well. Those are the things that I can measure really well that are easy to measure. Things that are hard are tangential velocities. Things moving left and right. I have a really hard time getting that velocity unless it's really close. I have a really hard time getting distances, which we'll talk about. I have a really hard time getting masses, which we'll talk about. Those things are all related. There's probably other things in here that I have a hard time with, but these are the big ones. So I'm going to talk today about 3 ways to measure distances. We'll talk about geometry, we'll talk about photometry, and we'll talk about velocity. Geometry is easy, big quotes for easy. It's not easy. You have a $1 billion satellite that's up in the sky taking pictures of everything very carefully. So it's only easy relative to the other things. Let's see. So geometry is accurate and correct. You don't need to know what the object is. You just need to know that it's there. And you can say, if the geometry works, then you know where that object is, regardless of what it is. But it only works for objects that are within the Milky Way. And if you want to do something that's actually that's very far away from us, then you have to have a $1 billion satellite that parks in the sky for 15 years and does a really good job. So there's a cool telescope called Gaia that's doing that right now, and it's getting distances to most of the stars in the galaxy. It's pretty sweet, but it's very, very difficult to do. Photometry means counting how bright something is. That's just brightness. Maybe brightness in different wave bands, but photometry is just brightness. So it's relative. You count photons and then compare with what you should have gotten. That's the tricky part. What you should have gotten. You have to know what that object is, and you have to know how much dirt is in the way. So those are 2 things that we have to get around. So you need to know what it is, and there's dust. And then the third one is velocity, which only works for distant objects. Got to get outside the local group. Things can't be gravitationally attracted to the Milky Way. Okay. So geometry. So the first one we're going to talk about is parallax. So this is easy to demonstrate. You just hold your thumb up over something and blink one eye and blink the other. If I do it right, I can cover up alternately one of you and then the other. If I were real smart, I could sort out how far away everybody is by that point. So it's just making triangles. And the sun goes around the Earth. It doesn't. The Earth goes around the sun. It's pretty useful that the Earth goes around the sun and not the other way around, because then parallax works. So as we're on one side of the year, so say this is the summer solstice, and then we go around over here to the winter solstice. Now we're 2 astronomical units away from where we started. Anything that's in the sky that has moved by a certain amount is a certain distance apart. So if our baseline is r, the distance to the object is d. P is what I measure. So I measure an angle P. That's how far something is moved on the sky. Now I got to have some really distant objects to be able to tell move relative to what. And then the distance, we just use a small angle approximation. The distance is just the parallax. Then we got to use some units to make it in the right units. So it's just the parallax divided by 1 degree, and that's in parsecs. This is the definition of a parsec. A parsec is something that when we move by 1 AU, it moves by 1 arcsecond in the sky. It is at a parsec. So that's the definition of a parsec. And that's the unit of distance that we use most often in astrophysics, because it makes the most sense. Light years are nice. We use light years sometimes, but parsecs are more useful. A parsec is like 3 light years. So this is pretty straightforward. It's just a geometry. So there's 360 degrees in a circle, 3,600 arc seconds in 1 degree, because there's 60 arc minutes in a degree and 60 arc seconds in a minute, just like an hour. So that gives you 3,600. Has anybody have any questions on that? Everybody happy? This is Gaia. It's really cool. It's going to keep going. I feel like I had something else to say. It just launched right after I started teaching this class, and now it's actually doing good stuff. But yeah, it's done a lot for improving our understanding of where we're at. Binaries are the second of 3 geometrical methods that we'll talk about. So this is, here now I've got a stick that's a certain length, and it's at a distance. Now if I can sort out what the length of that stick is, then I just have to measure what the apparent size is, and again I use trigonometry to sort out the distance to that object. So this is relatively straightforward. I've got this beautiful relationship that Kepler came up with. The period squared is 4 pi over the mass. G is just there for units. Times the semi-major axis cubed. The semi-major axis is the long axis. It's an ellipse. So you cube that, divide by the mass, and you get the square of the period. So you got to know what the mass of the stars are. But that's easy from spectra, relatively easy. So we get the masses from spectra. We get P with a clock. And then I'm left with the same thing that we did for parallax. The distance is just that angle in arc seconds in parsecs. So binaries are nice. Okay, the moving cluster method. It's useful for historical purposes because back in the day they didn't have a lot of techniques. I'm not going to worry too much about this, but I'm going to at least show you how it works so that you're sated. So if I have these stars, I want to measure the proper motion. Now I want to think about this fully in 3-dimensional space. So this only really works for the Hyades and maybe one other cluster that's close enough to actually measure the proper motion. Remember on slide 1 of this slide deck I said proper motion is hard to do. So you have to measure the motion across the sky of this thing over a period of several years. So it's a long measurement to do. And they have to be close enough that that period of several years actually matters. And they have to not be doing anything really crazy. You couldn't do this with the globular cluster because they're all dynamic will mess you up. So I got this cluster of stars, and they move over there. As they move further away, they get smaller and shift laterally. So this is where it was, and this is where it's going to be. How many of you did perspective drawing like this when you were a kid in high school? So, fair number. But does this make sense? So what you're doing is you're saying, I've got a point. All my parallel lines converge for the line, but all parallel lines converge to a point at infinity. So this line is parallel to this line in reality, but that doesn't mean good. But in perspective, it's shifted. So what we're going to do is we're going to use the fact that this thing is moving in this direction. I just need to know what this point is, and then from that I can sort out all of the geometry of where the stars are. So the stars start off here, they move over here. We can sort out where the fixed point is. Then we can sort out the angle that the stars are making in space, and you can sort out where they are in space. So you get the proper motion VT, which is just the distance times the proper motion. Sorry, the proper motion is the distance in arc seconds per second. That doesn't cancel out and make arc. The proper motion velocity is the distance times what you measure. What we want is d. So this is the important bit. This is how it actually works. Because the velocity, the tangential velocity, I can't measure. I can measure the proper motion, which is in angles per second. I need the velocity in kilometers per second. So I multiply by d. So I need to know what that d is. So I need to know what the ratio of vt and mu are. So I can't get that quite, but what I can get so now if I'm just looking at the plane, here's me, here's my star cluster moving in this direction, vt, vr. So this I can't measure. this equals u, which I can measure, times d, which is what I want. But I need to sort out what vt is. Now I can measure vr. Remember at the first slide I said I could measure radial velocities really well. So the radial velocity I know really well. And if I know where it's going, then I can sort out what the tangential velocity is. Make sense? So I measure from this perspective shift. From this perspective shift, I say it's here, it's here. I just continue that line all the way to the vanishing point. So now, here's me. Here's my cluster. It's moving this direction. So I know where the vanishing point is. I know where they're all going. That lets me get a vector that lets me get the direction of the velocity vector. And the velocity vector is parallel to my line of sight towards the vanishing point. I drew them at an angle here, but in reality they're parallel, because this is really far away. So what I need to know is the direction, and that gives me Vt over Vr. That gives me the angle here. So once I know the angle, then I know Vt over Vr. I can measure Vr, which lets me get Vt. I can measure mu, which lets me get d. Get all that? No? That's cool. We're going to move on. It's geometry. It's cool. It's fascinating. Totally worth downloading these slides, staring at it for half an hour until it makes sense. I don't care enough to spend any more class time on it. Forgot to do this first. Okay, so photometry, so to get distances photometry, we just exploit this relationship. Flux is luminosity divided by 4 pi r squared. And flux I can measure. L I need to know. And then I can get d, or r squared. So what I want is r. F is easy. L is really hard. But if I can get L, then I'm sorted. So, how's the distance modulus work? Let's talk about the distance modulus for a second. Okay, little m minus big M, apparent versus absolute brightness, is equal to 5 times the log of the distance in 10 parsecs, relative to 10 parsecs. So mu is the difference. That's called the distance modulus. Big M, I have to know what the object is to know what big M is. Little m, I just get out of my telescope. I just measure. So then the distance then, we just invert that equation. The distance is 10 to the 1 plus mu over 5 in parsecs. That make sense? So once you've sorted out little m and big M, then you make mu, then you just invert. So basic usage, so for Vega has an apparent brightness of 0.026. It's really small. It's close to 0. This is one of the brightest objects in the sky. Night sky, not the moon, not the sun. Outside of that, Vega. So its intrinsic brightness. This is what we measure is 0.26. Its absolute brightness. This is as if it were at 10 parsecs. Is 0.5. So does it get brighter or dimmer as you go from the apparent brightness to the absolute brightness? Little m or big M brighter? Little m.
Oh, little m.
Because it's this dumb upside downness right now. Okay, now there are very few objects for which little m is a smaller number than big M. Most objects get dimmer or get brighter when you put them at 10 parsecs. Some objects get dimmer when they're close. So this is one of the few objects that gets dimmer when you put it at 10 parsecs. So the distance modulus is apparent minus absolute, and then you just raise 10 to that and do a little algebra, and you get 7.5 parsecs. Yeah. Because it's closer than 10 parsecs. So the absolute is further away than it actually is. everything else, most other things, come in because there's really not very many objects within 10 parsecs of the sun. Now I'm running out of time. So hang on, if you're not sprinting, I'm going to finish this one thought. So what are we actually doing? You're solving this for d, but we're doing it in log. So little m is like log of the flux, and big M is like log of the luminosity. Negative log. Because it's all negative. Okay, I'm going to talk really fast about the reddening just so I get through it. This is LA before the EPA. So anybody that tells you that we don't need the EPA can cram it because it's ridiculous how important all of these environmental measures that happened in the 70s and 80s were. What's the difference between the top of this building and the bottom of this building? There's a bunch of crap in the way. It's not that it's further away. It's that there's a lot of stuff in the way. So extinction means there's stuff in the way. And interstellar dust is like smoke. So if I want to update my distance modulus, I got to add this A. This A tells me the extinction. This is how much further away it looks because of the crap in the way. Now I need to sort out what A is. I'll go through this again in a minute, but I want to just say it because this is one of those questions that everybody has. A is little m observed, that's what I measure with my telescope, versus little m actual. I have to know what the object is for that. And that's little m, that's the apparent brightness, actual with all the dust taken away. And this is, again, the total brightness, not in a particular band. Now, the color excess, E, B minus V, this is the excess of B minus V. I could have E, U minus R if I wanted, or B minus R, or all kinds of colors. This is the color that I measure minus the color that I know that object had. Does that make sense? So I see an A star, I know what color A stars are. I measure that A star, it's different. That gives me the color excess. Now, A is what I need, but it's impossible to measure. The color excess is relatively easy to measure if I know what that object is. And we want there to be a relationship between the total amount of light that I lose versus the amount of red light that I lose. So the amount of red light that I lose is going to tell me how much total light that I lose. So we want this relationship. A, the extinction, that's what I want but I can't measure, is equal to R, which is some number, talk about that in a second, times the color excess, which again I can measure. R, we're going to use 3. Because you got to use something. This is a number really, really difficult to get what this number should be. For a couple of measurements from the late 80s, this is 3. So people use 3 a lot. It's a lot of work on what this actually ought to be. But then, to include the extinction, with Vega, we have intrinsic, apparent brightness, intrinsic brightness, distance modulus, get rid of it, solve for D. With the dust, then without dust, this is for Andromeda, apparent brightness is 3.4, absolute brightness is minus 21. That got a lot smaller, didn't it? If Andromeda were at 10 parsecs, it would outshine the sun because it's enormous and 10 parsecs. That actually doesn't make any sense.
I think we'd be in it.
Because we'd be in it. Right? But anyway, it works. So we just subtract off this A. Okay, E, so we get the color excess from looking at the stars in Andromeda. It's a thing you measure. And then A is 3 times the color excess. And then I just subtract this A off my distance modulus to get the actual distance. Okay, now I'm going to stop talking. This is the tricky bit about using extinction. We'll come back. I'll pick up with this on Thursday. And I'm going to look. I think that I've now covered everything that's on the homework. So then the homework due date will stay put. Anybody have any other questions before I stop? Where is my doer?